on to the last section of Chapter 4 on antiderivatives. We're shifting gears a little bit and introducing a topic that'll play a big role in the fifth and final chapter of Calculus 1. So in this section, we introduce a process where we start with the derivative and kind of work backwards to find the function which would have that given derivative. A bunch of applications are based on this idea of differentiation backwards. In physics, for example, you might be given acceleration of an object, and then we know acceleration is the derivative of velocity, so we try to work backwards to find the velocity function. We know velocity is the derivative of position, and then we try to work backwards from velocity to get the position. So it would be an idea of differentiation backwards. The acceleration due to gravity at the surface of the Earth is a constant. That's how it's usually modeled, at least. And given that, you can find heights as a result of that acceleration, given initial velocities and initial heights. And we'll illustrate some applications along those lines in this section. First, as usual, some vocabulary. A function, capital F, will use sort of consistent notation of having capital F represent these antiderivatives and lowercase f represent the functions which we're anti-differentiating. So we'll try to stick, and largely will in the notes, to capital letters for antiderivatives and F and lowercase letters, usually F, for the functions themselves. So function capital F is an antiderivative of a function lowercase f if capital F prime of x equals lowercase f of x for all x in an appropriate domain. So when we differentiate f prime, when we differentiate capital F, we get function f back. So capital F is an antiderivative of f. Going to the relationship from f to its derivative, capital F to its derivative, lowercase f, that's what we've been doing. So we're trying to do this process backwards and extract capital F from the known derivative, lowercase f. The most general antiderivative, and I will describe this usually as a set, calling attention to the word set. It's a set of all antiderivatives. The book won't use that terminology, and you're highly unlikely to see that terminology elsewhere, but it's a good terminology. We're treating the set of all antiderivatives is called the indefinite integral of f with respect to x, and we'll encounter definite integrals in chapter 5. But indefinite integral of lowercase f is the set of all antiderivatives of lowercase f. A function can certainly have more than one antiderivative, as we'll illustrate. And we'll use this notation to represent indefinite integrals. The integral sign, the stretched out s, is called an integral sign, and its genealogy really is, it's an S that's been stretched, and it's S for some reasons to be made a bunch less obscure in chapter 5. But for now, that's the integral sign. The function which we're anti-differentiating, the lowercase f, is called the integrand of that indefinite integral, and x is the variable of integration. So for now, we're just taking this as representing the most general antiderivative, or if you like, the set of all antiderivatives. We'll illustrate it with some examples and get some clean notation here in a second. By corollary 4.2, the functions with the same derivative differ by a constant result. FYI, it was a corollary to the mean value theorem. We see if we've got any two antiderivatives of the same function, they must differ by a constant. That's exactly what corollary 4.2 said only it didn't speak in terms of antiderivatives, but it dealt with functions and their derivatives, and that's what we're doing as well. So the indefinite integral of a given function f can be expressed always in this form. Capital F of x plus c, where that capital F is some antiderivative, and we're using the plus c as a shorthand notation for a set of functions. So that's the way I'm introducing the terminology. This idea of speaking of sets is probably fairly rare, but you have to interpret indefinite integrals as sets of functions or collections of functions. You can't just treat it as a single function because it's not a single function. So when we speak of the indefinite integral of f of x dx, is how I read that, this represents the set of all capital F of x such that, little vertical line means such that, capital F prime of x equals lowercase f of x for all x in the domain of lowercase f. And we're introducing this notation. Now this is a common notation here, representing that indefinite integral as capital F of x plus c, plus capital C. The plus capital C is shorthand for the set of antiderivatives. Sometimes the terminology arbitrary constant. Capital C represents an arbitrary constant. It represents the fact that we got a whole collection of functions. We got a whole set of functions, not just any functions. They're functions of a particular sort. Those functions, such that when I differentiate them, we get the integrand, lowercase f, back out. Sometimes we'll deal with indefinite integrals and sometimes we'll deal with antiderivatives, and they're different things. When we want a specific value for the constant, we'll use a letter lowercase k to represent specific fixed constants versus this arbitrary constant stuff. So be very careful with this. Indefinite integrals are entire collections of functions. What they are is they're the set of all antiderivatives of function lowercase f, and that's what these symbols mean. So this is a collection of functions of a particular form, not just a single function. We will wish to work problems and we will need single specific functions. Well, when we do, we'll add a plus k to some antiderivative. We'll illustrate this with examples. But be careful, there's a difference between antiderivatives and indefinite integrals. An antiderivative is just some function, capital F, satisfying this relationship with lowercase f. But an indefinite integral is an entire collection of functions, each of which satisfies this relationship. When you hear collection, saying set's a little cleaner way of dealing with it. And that's why I've described it in terms of set verbiage. So we get the following. If capital F is an antiderivative of lowercase f on an interval I, then the indefinite integral of lowercase f on this interval is capital F of x plus c, where c is an arbitrary constant. It bothers me a little bit to write it like this, but I have clearly stated that that represents an entire set of functions. It's the set of all antiderivatives is what it is. You take a physics class, they'll probably use this type of verbiage, arbitrary constant. You take additional math classes, like differential equations we're about to chat about, it's likely they'll use some type of verbiage along those lines as well. But indefinite integrals are not functions, they're collections of functions. They're sets of functions. They're sets of antiderivatives. Let's do an example, 4.8.2. Okay, you're asked to find an antiderivative of a given function, and you want it to satisfy the condition capital F of 1 equals negative 1. So this is a question about antiderivatives. It's not explicitly a question about indefinite integrals, but we're going to approach it in terms of indefinite integrals because the indefinite integral is a set of all antiderivatives. So that thing, lowercase f, it's got a whole bunch of antiderivatives. We're looking for a specific one that satisfies this condition. Okay. Now, we don't have just yet an organized way to find antiderivatives, but I think you can probably guess what we would differentiate to get 3x squared. We would differentiate x cubed to get 3x squared. That checks, right? So capital F of x equals x cubed is an antiderivative of the given function, lowercase f of x equals 3x squared. So we know if we look at the indefinite integral of f of x, if we look at the indefinite integral of x cubed, then we get, as we just stated, some antiderivative plus an arbitrary constant, capital C. So the indefinite integral of this function is x cubed plus c. It's all functions of the form x cubed plus some number, some constant. The constant could be anything. So capital F of x that we're looking for up here must be of the form x cubed plus k for some constant k. The desired antiderivative f must be of this form. Now we need to figure out what the constant k is. Slight abuse of notation. I've called uppercase f of x, x cubed here, and down here we've used the same name for x cubed plus k, so that's on me, that's bad. We're in this situation because, well, that function 3x squared, it's got a whole bunch of antiderivatives. I have maybe abused the notation a little bit. I don't really want to go overboard with notation of using the same letter to represent potentially two different functions. We're looking for a function capital F of this form. So we need to figure out what the k is. So here I'm choosing a specific function, not a set of functions. That's where I'm shifting from the plus capital C to the plus lowercase k. That's my consistent way of dealing with this, to try to avoid confusion between indefinite integrals and antiderivatives. They're different things. I chose this one because it's an example in the book, and they give us a picture I can refer to. Figure 4.55, given here on the right, gives a graphs of such functions. Functions of the form x cubed plus k for various values of k. The book is not adhering to my use of the lowercase k, and they've said c takes on different values, but it's the same idea. So were we to take x cubed, looks like x cubed minus 2, we'll get this red curve, which is the one we're looking for. If we were to take x cubed itself, taking the constant to be 0, we get this y equals x cubed curve that passes through the origin. So they've graphed a bunch of these different functions. They all have the same shape. They're all y equals x cubed functions. They just had different constants added to them, and that results in the vertical translations. Well, we want, because they told us we want, capital F of 1 to equal negative 1. Graphically, that means we want from this collection of curves the one that passes through the point x, y equals 1, negative 1. Here's the point 1, negative 1. This is the one we want. So we just need to figure out what the value of k is that produces that one. And they've really given it away in the picture. But let's do the algebra, because we might not always have pictures. We're requiring f of 1 to be negative 1. So we want a value of k that makes the graph of the function y equals capital F of x contain the point 1, negative 1, as given in the figure. Algebraically, f of 1, I know capital F is of this form. Plug in x equals 1, we get 1 cubed plus k, 1 cubed plus k, and we want that to equal negative 1. So we'll set that equal to negative 1. Simplifying, that's 1 cubed is 1, 1 plus k equals negative 1. Solving for k, we get k equals -2. So we need capital F of x to be of this form where k is -2. That's what we need right there. So capital F of x must be this function. Simply saying find an antiderivative isn't enough because there's a whole bunch of antiderivatives. Here's a picture of like 5 different antiderivatives graphed right here. We're looking for a specific one. If you're told to look for an antiderivative, you can't specifically answer that. Well, you can find an antiderivative, but which one do they want? It comes with a layer of vagueness. That's the plus, what constant you add to it. It's the plus capital C part that's the vagueness. But they've given us additional information. And with that additional information, we can tie down what constant we should add. So there's a geometric approach to this idea. And the last 2 or 3 lines down here gives the way to algebraically translate that given information into information about finding the constant. Okay. This example we just looked at is an example of a differential equation, usually abbreviated DE for differential equation. It's a specific type called an initial value problem. And the differential equations, folks, they like their acronyms, and they often abbreviate initial value problem, IVP. There's boundary value problems, BVPs, and other settings as well. But anyhow, in it, we were given the derivative of the desired function. We were given the derivative was 3x squared, and we were given the value of that function at some point. It was the fact that when we plugged 1 into the function, we got -1 out of the function. Could be interpreted graphically, as we saw. Being given that information is being given an initial value. So that's the reason these are called initial value problems. They gave you the derivative and they gave you a value. They call an initial value. That is a point that the function itself passes through. So to solve the differential equation is to find the function that has the given derivative and takes on the given value at the given initial x value. So you're given the derivative and you're given an initial condition, a point on the curve. To solve the differential equation is to find the function that has the given derivative and when graphed passes through the given point. Differential equations, in some sense, a lot of the applications of this calculus stuff are related to differential equations. It's touched on in our calculus book. Certain differential equations are discussed in Thomas's calculus in chapter 9. They look at first order differential equations. You would likely do that in calculus 2. Chapter 17, they look at second order differential equations. And you might not quite get all that material in this gigantic book covered in a calculus sequence. The chapter 17 stuff you might not cover. If so, it would be calculus 3. We have an entire class, as does every university, devoted to differential equations. If you're in math, physics, engineering, conceivably chemistry, physical chemistry, deals with rate equations, which are just differential equations, it turns out. It's likely you've got a differential equations class in your future if you're in one of the STEM areas, basically. In biology, population growth models come to you as differential equations as well. At ETSU, the class is differential equations. It's Math 2120. The catalog description, as of today at least, says offers first order differential equations and applications, second and higher order linear differential equations and applications, Laplace transforms, and systems of differential equations. Yeah, this last part, systems of differential equations, could be a bit of a challenge unless you've had some linear algebra. And I don't think linear algebra is currently a prerequisite for our differential equations class. So yeah, you may or may not cover differential equations. May or may not cover systems of differential equations in the sophomore class. It's good stuff, you just may not have the appropriate background the way the curriculum's currently laid out. We'll look at differential equations a little bit more. It's the time to do it when we start learning how to anti-differentiate. Okay, so what do you know about antiderivatives first? Well, it's differentiation backwards. So anything you know how to differentiate, you take that, write it out backwards, and have a formula that relates to antiderivatives, and so a formula that relates to indefinite integrals, if you respect the notation. Table 4.2 gives 13 indefinite integral formulas. Now, all these things are some differentiation formula written kind of backwards. For example, equation 1 says the indefinite integral of x to the n is x to the n plus 1 divided by n plus 1 plus an arbitrary constant. You have an indefinite integral, you better have a plus c on there to indicate that these are not functions, but entire sets of functions. Oh, we can't divide by 0, so that puts a little condition on the exponent n. Why is this true? Because if we'll differentiate this, forget the plus c, take an antiderivative, an alleged antiderivative, take this, differentiate it, and it'll produce that. Yeah, if you differentiate x to the n plus 1 divided by n plus 1, you'll get x to the n back. Right, the exponent would come down as a coefficient. By the way, it'd cancel with what's in the denominator. You'd subtract 1 from the exponent, and you'd be left with x to the n. So if differentiating this produces that, then the indefinite integral of that is the aforementioned this, plus an arbitrary constant, provided nothing goes wrong. So avoid the division by 0 stuff. And so forth. You know how to differentiate sines and cosines. So that produces some indefinite integral formulas. You know how to differentiate, you know how to differentiate all the trig functions. You know how to differentiate tangent, cotangent, secant, cosecant. So those differentiation properties have corresponding indefinite integral properties. These are simply differentiation formulas written backwards. Maybe let's look at number 4 that catches my eye. They've written this up where they've got constant multiples of x in almost all of these in this list, taking the constant to be k, not to be confused with the k that I introduced above as some specific constant that we're trying to find for specific antiderivatives. Here, just a constant multiple. They've commonly used k for that. If we differentiate tangent of kx, derivative of tangent is secant squared. So we differentiate the tangent, producing the secant squared, rewrite the inner, and multiply, chain rule says, by the derivative of the inner. The derivative of kx is k, and that's why there's a k out front. So if we were to integrate secant squared kx, we'd get the tangent kx. Oh, that's in the way. I'll have to put that over here as a reciprocal. So we get 1 over k tangent kx from this one. What do you know how to anti-differentiate, or what do you know how to find the indefinite integrals of? Sines, cosines, and the other stuff that was derivatives. We haven't done antiderivatives of secant, but we know the derivative of tangent is secant squared, so we know how to anti-differentiate secant squared and cosecant squared, because that's related to the derivative of cotangent. There's some negative signs to process in this. You differentiate secant, you get secant tangent. All right, then I know how to anti-differentiate secant tangent then. And similarly for cosecant cotangent. It turns out anti-differentiation is a way more involved process than differentiation. You know as much as anybody at this stage about differentiation. You're good to go. As far as anti-differentiation goes, you'll spend about half your time in Calculus 2 learning techniques of anti-differentiation, techniques of integration. It'll ultimately be called, because these are indefinite integrals. And even then, there'll be things I could easily make up that, in a sense, you can anti-differentiate. Nothing personal. Anti-differentiation is hard. It's possible to make up things that can't be anti-differentiated, in a sense. So we're just doing differentiation backwards. You're really good at differentiation. At the end of Calculus 1, you're a little weak on anti-differentiation. You haven't been exposed to too much stuff yet. Funny story, at the end of Calculus 2, you'll still be a little weak at anti-differentiation. You'll know as much as anybody else, but in some sense, a lot less is known about anti-differentiation than is known about differentiation. That's one reason we got classes in differential equations. We got more classes in differential equations. Applied math probably leans heavily on differential equations. We've got classes in numerical techniques. Yeah, because you got these functions you can't analytically anti-differentiate, so you do numerical approximations. This integration stuff is and it's simply harder than differentiation. You're good at differentiation. Kind of, in some sense, nobody's that good at anti-differentiation. I can make up things easily that can't be anti-differentiated, in a sense. Give me a little disclaimer there. We had differentiated exponential functions, meaning I can get indefinite integral statements related to exponential functions, as well as log functions, as well as inverse trig functions, and finally, copying these in the same order that the book did, exponentials to bases other than e. We could also deal with logarithms to bases other than e as well. They didn't include that in the list, so neither did I. But here's a list of 13 things, 13 formulas. They're all cluttered with this, these k parameters. I think it's a little bit cleaner just to set k equal to 1. And these look a touch more familiar. The derivative of tangent is secant squared, then the indefinite integral of secant squared is tangent plus a constant. The derivative of secant is secant tangent, then the indefinite integral of secant tangent is simply secant plus a constant, and so forth. The derivative of the natural exponential function is itself, then the indefinite integral of the natural exponential function is itself plus a constant. So here's a statement. This is not explicitly mentioned in the book, but what we have here is the same thing we had in the previous table, except I've set k equal to 1. I think this is a little bit easier to follow. We'll quote some of the things upstairs when we go through the problems, because we will have k's in the way. But all these k things, you know how to do the differentiation. It's going to require the chain rule and multiplying by the derivative of the inner. So it throws on an extra factor of k. That's why there's a 1 over k over here to do some cancellation. As we saw in that first example with the 3x squared thing, it was some idea of that. So this is one convenient thing. What do you know about anti-differentiation? You know this. The stuff here is exactly what you know about anti-differentiation. At the end of this class, you'll have one technique of integration. It's called U substitution. And it's a little trick involving the chain rule and then one of these 13 things here. So I can conveniently entirely put my hands on exactly what you know about indefinite integrals, about antiderivatives. A note, let me give it my own little number here because we're going to refer to it quite a bit. Based on the properties of differentiation, we get the following properties of indefinite integrals. Linearity rules, I call it. I'm not sure the book uses that verbiage. It's the right thing to call it because it deals with linear combinations. We have a sophomore level class on linear algebra as well. Linear is good. You've got techniques to do linear things. Nonlinear is tricky. And techniques to deal with nonlinear things are, there's some there, but they're a lot more scarce than techniques to deal with linear things. So in a setting where we're supposing capital F is an antiderivative of lowercase f, capital G is an antiderivative of lowercase g, and k is a constant. We're going to look at indefinite integrals. So this constant k is not being used as a plus k type thing. It's being used as a constant multiple inside integrals, for example. The constant multiple rule for indefinite integrals says the indefinite integral of k times f of x is k times the indefinite integral of f of x. If you want to write it in that set notation, or the abbreviation for that set notation, we'd write k times capital F of x plus c. So you can bring constants outside of indefinite integrals, is what this says. The indefinite integral of the sum or difference of lowercase f and lowercase g is ultimately the sum or difference of their antiderivatives plus an arbitrary constant. So we're getting indefinite integrals of sums to be sums of indefinite integrals integrals of differences to be differences of indefinite integrals. The book actually puts these properties in a table and lists those tabular as well in the book. Okay, let's do a whole bunch of examples. What we'll do is continually come back to what we know about antiderivatives. So let me shrink it a little bit. Let's get maybe this running in the background. So we'll have to come back and refer to this table. You'll get this in your head because you'll use it so much. And let's look at a whole bunch of examples. Next, exercise 4.8, 0.2, 0.10, 0.14, 0.18, 0.20, and some pieces of those. Just a hodgepodge of finding antiderivatives. So find an antiderivative of each function. Check your answers by differentiation. Okay, these we're largely just going to kind of poke at and guess what's going on. We do have that table to give us more confidence, but for now, let's just poke at them. These will be fairly elementary. X squared, they want an antiderivative of x squared. An antiderivative of x squared must involve x cubed. Because when you differentiate it, you'll subtract 1 from the exponent, you'll have some x squared stuff. Actually, when you differentiate x cubed, you get 3x squared. We don't want 3x squared, we just want x squared. Well then, let's divide by 3 up here, and let's consider not x cubed, but x cubed over 3, I guess I should say divide by 3 down here. X cubed over 3, then when we differentiate, checking it by differentiating, the derivative of x cubed over 3, 3x squared over 3, the 3's cancel, x squared, there you go. So indeed, that is an antiderivative of x squared. 1/2 x to the negative 1/2, okay, same stuff. I would expect to, add 1 to the exponent? If we add 1 to the exponent and x to the negative 1/2, that'd give us x to the positive 1/2. Okay, let's differentiate that because I'm worried about this 1/2 out front. If you differentiate x to the 1/2, you get 1/2 x to the subtract 1, negative 1/2. That's why we added 1 over here. To undo that, we're going backwards. Oh, and that's exactly what they wanted us to anti-differentiate. So it must be that x to the 1/2 is an antiderivative of 1/2 x to the negative 1/2. I should probably emphasize, we're looking for antiderivatives. We're not looking for indefinite integrals. If we were, we'd have to do this plus c stuff. That wasn't the question. This was fine, an antiderivative. And we're finding the simplest antiderivative. There's plenty others of them out there. I could add 7 to both of them. And when I differentiated, the derivative of 7 is 0, so we'd still have antiderivatives. So let's find antiderivatives and wink the simplest antiderivative without getting into the plus a constant stuff. They just wanted an antiderivative. So that's the plan. When dealing with powers of x, we'll add 1 and then try to fudge things to make sure we get the correct coefficients. How about some trig functions? Okay, well, if they want us to anti-differentiate pi halves cosine pi x over 2, I'd expect to use what? Sine, derivative of sine is cosine. So let's take a sine function. Let's take sine of pi x over 2, the same argument inside the trig function. So let's try that. We'll differentiate that and then make adjustments if necessary to deal with the coefficient, just like we did with the powers of x on the previous slide. So differentiate sine pi x over 2. Derivative of sine is cosine. Rewrite the inner. Chain rule says multiply by the derivative with respect to x of the inner. That's pi over 2. That's the same thing we were looking for. So an antiderivative of this function must be this function, sine pi x over 2. If the pi over 2 wasn't there, we'd have to make some adjustments because we're getting a pi over 2 from the chain rule out front. So we'd have to adjust this appropriately to get cancellation with the pi over 2 if this pi over 2 weren't here. Similar to what happens in the next one. They want an antiderivative of 4 secant 3x tangent 3x. All right, well, an antiderivative of secant tangent is secant. Derivative of secant is secant tangent. So let's try secant. Let's try secant 3x because these two functions have 3x in them. So let's try secant 3x. When we differentiate secant 3x, derivative of secant is secant tangent. The inner stays the same, 3x. So far, so good. Chain rule will tell us multiply by the derivative of the inner function. So you pick up a 3, and we get 3 secant 3x tangent 3x. That ain't what we want. Okay, we can still fix it. We got the trig functions, we're just off by constant multiples. So we need to introduce a factor of 4, and we need to eliminate this factor of 3. So how about we divide out by 3, introduce a factor of 4. Let's take 4/3 secant 3x tangent 3x. Then when we differentiate, we'll have 4/3 out front. Differentiate. Oh, excuse me, I got an error here. I should not have the 3x. Let's take 4/3 secant 3x. When we differentiate 4/3, error, secant 3x, then we'll get, we'll fix this in the notes, the tangent 3x stuff should not be here. I'm simply taking what we had and multiplying it by 4/3. Yeah, so the tangent 3x should not be there, typos. Differentiate, forget this, the secant 3x, we got the 4/3 out front, derivative of secant is secant tangent, so this tangent should be here. Chain rule spits out a 3, just like we had upstairs, right? When I was differentiating the secant, we got this. So I've cut and pasted incorrectly. We pick up a factor of 3. Hey, the 3 cancels with that 3, leaves us with a 4. So the correct answer is, excuse me, correct answer is 4/3 secant 3x. Forget the tangent 3x. I messed up on that one. I'll revise this in the notes. So it's the same strategy of, well, I recognize this as a derivative of something. So let me take that something and play with it until I can get the parameters balanced. That's the approach we're taking at this stage. We'll have an organized way of doing it when I start appealing to the table. How about an exponential? E to the negative x over 5. Well, an antiderivative of e to the x is e to the x. So let's just see what happens when we differentiate e to the negative x over 5. Differentiate, rewrite. Right, the derivative of the exponential is itself, so it gets rewritten. Rewrite the inner. And the chain rule says you'll have to multiply by -1/5. Producing this, that's not what we want. We need to get rid of that negative sign and that 5. So let's take this function and revise it by multiplying by -5. Did it work? Check by differentiation. That was their rule. Differentiate -5 e to the -5x. The -5 just acts as a constant multiple. Differentiate the exponential, nothing happens. Rewrite the inner, multiply by the derivative of the inner, you get the -1/5. The 5's cancel, the -1's cancel, you get that back. That's right. So there is an antiderivative of the given function. Because we recognize some things as derivatives, and before Calculus 2 is over, you'll have a lot more robust techniques than just kind of eyeballing it and guessing, but that's all we've got right now. We recognize certain things as derivatives. So we take those things and try to find functions such that when I differentiate them, I get the given function. Exponential functions, I'm going to use exponential functions. Sines, I'm going to use cosines. Cosines, I'm going to use sines. I'll maybe off by some negatives in there. Secant tangents, derivative of tangent is secant tangent. I'm sorry, derivative of secant is secant tangent. So we had an illustration where we had a secant tangent. We wanted an antiderivative. We looked to secants. What about tangent? Can you integrate tangent? Is that the derivative of something? I don't think tangent is. Maybe tangent squared. We'll run across some tangent squared stuff here shortly. It'll involve a trig identity and some trigs. All right, so let's now appeal to the table. So let's do these a little bit more organized. Find the indefinite integral of 1/5 minus 2 over x cubed plus 2x. Okay. We know the indefinite integral of a sum or difference is a sum or difference of the indefinite integral. So we can break this into 3 indefinite integrals, sum or difference rules, as we stated. We can bring constants out. Let's bring the 1/5 out, the 2, bring those constants out, constant multiple rule. That was the other rule in note 4.8a. Next, that gives us powers of x. Excuse me, x to the 0. I can get from the table with n equals 0 in that first list in the table of adding 1 to the exponent, giving us an x to the 1. Of course, the derivative of x is 1. X to the -3, we'd add 1 to the exponent and divide by the resulting exponent. We'll look at the table in a second. X to the 1, we'll add 1 to the exponent, giving us 2, divide by 2. And I'll owe you a plus a constant because this is an indefinite integral. This comes from table 4.2 part 1 with n equals 0 here, n equals -3 here, and n equals 1 here. Oops. Simplifying a little bit, let's see, -3 plus 1 is -2. The -2's cancel, leaving us with an x to the -2, right? The 2's cancel here, leaving us with an x squared. So here's what we get written as powers of x. If you want to take that -2 and write it as a quotient, there you go. If you don't, then, well, then there you go, whichever. I wrote it like this because they gave it to us like this. And like I said, let's look at table 4.2 and make sure we're doing this right. So we were dealing with powers of x. Table 4.2, part 1 says when dealing with a power of x, simply an x to the n, add 1 to that exponent and divide by that new exponent. Yeah, because when you differentiate, you bring the exponent down as a coefficient and then you subtract 1. So instead of multiplying and subtracting, over here, we're dividing and adding. We're going backwards from the way differentiation is performed. So that's exactly what we did. For example, there was an x to the -3, and we took n equals -3. Then we get a -3 plus 1, and a -3 plus 1 here, and that's where the -2's came from. Right here. -2 in the exponent, -2 in the denominator. Let's do another one. Okay, this one's a touch more interesting. Actually, not a lot to show because I'm going to use table 4.2, part 3 with k equals 5. We want to integrate 3 cosine 5 theta d theta. First, we can bring the 3 out front. Why is that? Constant multiple rule. In note 4.8.a, we bring constants out front of indefinite integrals. How do you integrate cosine 5 theta? Well, here's how you use that table. That table would tell you how to integrate cosine of k times theta. Apparently in part 3, let's look at that. In part 3 of the table, they have the integral of cosine k times x. That's what we have where k is 5. Then they get sine kx over k, plus a constant, of course, it's an indefinite integral. So we'll get sine 5x divided by 5. So the table tells us we get sine 5 theta divided by 5, plus a constant, still got the 3 out front, and that gives us 3/5 sine 5 theta, if you simplify it a little bit. They have to ask us very specific indefinite integral questions, because if it ain't in table 2, table 4.2, we can't do it. Unless maybe we can take what they give us and turn it into something in table 4.2. Let's do one with exponentials. Indefinite integral, 2e to the x minus 3e to the negative 2x. All right. Integral of the difference is the difference of the integrals. You can bring the constants out front. I'm boring with this level of detail at this stage, really. But we can isolate then indefinite integral of e to the x. What do you differentiate to get e to the x? E to the x. How about this? Here we've got e to the constant multiple of x, and that constant's negative 2. Let's look in table 4.2. Apparently it's the 8th formula, and see what we get there. Formula 8 says when we integrate e to the kx, we get 1 over k, e to the kx. There's y. Just as the chain rule would force you to multiply by k in differentiating, we divide by k because we're anti-differentiating. So it's related to the chain rule backwards. So here's what we need for the indefinite integral. We had k was negative 2, wasn't it? So we'll have 1 over negative 2 e to the negative 2x. Divided by negative 2 e to the negative 2x. So there's exactly what we get when k equals negative 2 in that formula. Of course, an antiderivative of e to the x is e to the x. If you want some documentation, take k equals 1 in the table in the same equation. But that produces this. Don't forget the plus c. It's an indefinite integral, so we've got the plus c taken care of. We can clean this up a little bit, not much. I can drop the parentheses and do something with negative signs. So there's what we get for the indefinite integral of that function. So it's a matter of finding the integrand in the table. Here's an exponential, not base e. Integral of 1.3 to the x power. Okay, we got something in the table that deals with a to the x power. Apparently so. It's the last thing in the table. We've got, let's see, we got a number to the kx power. Is that what we had? We don't have a, where do I look? Here we go. We don't have a k. We've got a, the base is 1.3, and the exponent's just x itself. So I guess I could say we can use the table with k equals 1, or better yet, let me scroll down to the table where I plug k equals 1 in all of them. Here's exactly what we have then. So equation 13 with k equals 1 gives us this. And this is what we have. We got a to the x power where a was, for some reason, 1.3. Then we should get 1 over the natural log of 1.3, 1.3 to the x power, plus a constant. Remember how you differentiate exponential functions, base a. You have to throw on this extra natural log of a part. That's what was natural about the natural log functions and the natural exponential functions. So if we had base e, this term I would still be there, just be 1, so we wouldn't write it. But here we have base other than e, so we pick up the natural log. It's not the chain rule, it's the weird behavior of exponential functions that aren't base e. that they produce when you differentiate them, these extra constants. All right, well, our constant is 1.3, so we'll get 1 over natural log of 1.3 times 1.3 to the x power. No real details to show. We get 1 over the natural log of 1.3, 1.3 to the x power, plus c, of course, because it's an indefinite integral. I can write it like this if you like. All right. Here's one that's a little more interesting, though. Integrate 2 plus tangent squared theta d theta, tangent squared. Let's look in the table for tangent squared. Okay, there's exponentials. There's some stuff involving inverse trig functions, logs, exponentials. Here's the trig functions. They run from 2 to 7. And I don't see a tangent squared. We got a secant squared. We got a cosecant squared. We don't have a tangent squared. So we simply can't do that one. But they gave us a hint. If it ain't in this table, we can't do it. Well, that ain't in the table. We can change that to something that is in the table, and then we can do it. And the book gives a hint on this one. They say, hint, 1 plus tangent squared theta equals secant squared theta. So we could take this tangent squared and write it as secant squared minus 1. Then we need to integrate secant squared. Secant squared's in the table. If it ain't in the table, at this stage, you can't do it. So, we don't yet know how to anti-differentiate tangent squared. Actually, if I followed closely through this, we'd see how to integrate tangent squared, how to anti-differentiate tangent squared. But we do know how to anti-differentiate secant squared. Yeah, secant squared is a derivative of tangent. So an antiderivative of secant squared is tangent. Okay, so we'll take what they've given us, take the tangent squared, let's solve this for tangent squared. We get tangent squared, then take the 1 to the other side as secant squared theta minus 1. Okay, substitute that in for tangent squared. Simplify a little bit. 2 minus 1 is 1. We got a secant squared here. Indefinite integral of the first plus the indefinite integral of the second, sum rule. You know how to integrate 1. Antiderivative of 1 is the variable, variable's theta. And you know how to anti-differentiate secant squared. The antiderivative of secant squared is tangent. As we observed up here, you can also see it from the table. It's equation 4. We've got simply secant squared. Let's look at equation 4. This is the table with k equals 1. Integral of secant squared is tangent. Awesome. So we produce a tangent, and there's really no simplifying that. So there's an integral of that particular function. If it ain't in the table, you can't do it. Or at least, if it ain't something you can turn into stuff in the table, you can't do it. Another one, okay, this is a question that's asked a bit differently. They say verify this indefinite integral formula. All right, so we can figure out what this means. I think we can do it. They didn't ask us to find an indefinite integral. They've given us an alleged indefinite integral. And they want us to verify that they've done it right. Well, first off, an indefinite integral is a set of functions. So if I take some function in this indefinite integral, remember this indefinite integral is written like this, x over x plus 1 plus c. So there's their rumored version of this set. That means this particular function must be of the form f of x equals x over x plus 1 plus some specific k. Specific function, specific k. Not arbitrary constant, specific constant. I don't know what it is just yet. Here, it could be a whole bunch of different things. This represents an infinite number of things, actually represents all real numbers. We could add anything. I want a specific function because I can't differentiate sets, but I can differentiate specific functions. Here's your specific function. An abbreviated version of this is Hey, indefinite intervals are sets of antiderivatives. I may not be that good at anti-differentiating, but I can differentiate. So you give me an alleged antiderivative, I can check this just by differentiation with appropriate respect paid to the notation. So we've picked a particular function in this indefinite integral set. It must be of that form. If we differentiate this and we get the integrand, then we've done it right. So differentiate this, no problem, it's a quotient. I'm good at differentiating. For that quotient, we'll have derivative of the numerator is 1, denominator x plus 1, minus numerator x, derivative of the denominator x plus 1, derivative is 1 over the denominator squared, plus the derivative of the constant k is 0. Simplifying, dropping the square brackets and the 0 gives us x plus 1 minus x, right, over x plus 1 squared. The x and negative x cancels, gives us 1 over x plus 1 quantity squared. That's the integrand. So all I got to do is explain now. So this capital F of x is an antiderivative of 1 over x plus 1 quantity squared, because when differentiating it, we get this value here. So by theorem 4.8, the indefinite integral is of the form some specific antiderivative plus a constant. So we'll take this specific antiderivative and add an arbitrary constant. My little specific constant, I need it up here, but it got differentiated away anyhow. I'm absorbing that in the plus c. This represents adding arbitrary constants. So absorb the k in that arbitrary constant. If you don't like that logic, it's a little sloppy, but that's a standard way to treat it. So we are getting exactly this out when differentiating an element of this set, and that's what the statement means. Being given an indefinite integral is basically being given antiderivatives. How do you check that it's right? By differentiating those alleged antiderivatives and making sure the differentiation gives what it should. Differentiating this should give that, and it does. Back to the notes. Okay, we went through that pile of exercises, some more ideas on differential equations. So we'll go through and use this in solving initial value problems. Formally, a differential equation is an equation relating an unknown function, y, of x, and one or more of its derivatives. The functions whose derivatives satisfy a differential equation is called a solution to the differential equation. The set of all solutions is called a general solution. When they talk about sets of all solutions, at this stage, we'll get those by using the technique of indefinite integrals. That produces sets of antiderivatives. So we'll get general solutions to differential equations by considering indefinite integrals. The problem of finding a specific solution y of x, which is a solution to the differential equation, and satisfies certain initial condition or conditions by giving you a value of the function at a point, the value of the derivative at a point, the value of the second derivative at a point, and so forth, is called an initial value problem. All right, now differential equations can involve derivatives. It says one or more of its derivatives. Could involve second derivatives, could involve third derivatives, and so forth. So these could involve higher order derivatives. When they do, you're going to need more initial values. In Calculus 1, it's almost exclusively first order derivatives. And it's going to have to be something you can handle with table 4.2. In this batch of examples we're about to do, I think a second order differential equation is included, one involving second order derivatives. I think it's probably the last one, or the second to the last one. And they'll have to give us two initial conditions. We'll be able to do it because of the type of question they've asked. But differential equations can be extremely hard to solve. We got an entire class on just solving differential equations. Not near the ones we get in here. They'll be set up for us to do with the knowledge we have. Okay, an initial value problem. Suppose dy dx equals 9x squared minus 4x plus 5, and y of negative 1 equals 0. Find the function y satisfying this differentiation condition and passing through this point. This is the differential equation, and this is the initial condition. The two pieces of information together are called an initial value problem, just to get you some cumbersome vocabulary. It's an IVP, to use some acronyms. Okay, so let y equal f of x be the function we're looking for, so that when we differentiate that function, we get 9x squared minus 4x plus 5. All right, so the desired function is an antiderivative of 9x squared minus 4x plus 5, or using our notation for indefinite integrals, the desired function is an element of this indefinite integral. So let's find this indefinite integral. Indefinite integral of this second degree polynomial. Can use the sum or difference rule and bring the scalars out front. We've used the sum or difference rule and the constant multiple rule all in one step. I don't think we need that level of detail anymore. So we've actually used two steps here. Can you anti-differentiate x squared? Yeah, add 1 to the exponent, getting x cubed, divide by that 3. X, add 1 to the exponent, divide by what you get. 1, technically add 1 to the exponent, divide by what you get. Of course, it produces x. And then you owe me a constant because it's an indefinite integral. Indefinite integrals always have the plus c on them. Good way to lose a point on a test is to do an indefinite integral and leave the plus c stuff off. That's not right. They're not even the right things. Without the plus c, you've got a function. And indefinite integrals are not functions. They're sets of functions. That's what the plus c indicates. So don't forget the plus c. It matters. You couldn't solve this initial value problem without it, in fact. Let's clean it up a little bit. 9 divided by 3 is 3. Do some cancellation there. So we produce this for the indefinite integral. So f of x is an element of this set. So f of x is of the form 3x squared minus 3x cubed minus 2x squared plus 5x plus some specific constant. F itself, I'm going to change the c into a k for reasons explained previously. It's a specific constant. What constant is it? Well, that's where this information comes in. So we found not f of x, but the form of f of x. Once we find k, based on the initial condition, we'll know f of x specifically. All right, so we left off with this information on the last slide. We use the initial condition, y of negative 1 equals 0, y of negative 1, or f of negative 1 equals 0, to find k. All right, what happens when you plug negative 1 into the function? You get 3 times negative 1 cubed minus 2 times negative 1 squared plus 5 times negative 1 plus k, and you should get 0 out. So we'll do exactly that. Plug the negative 1 in, produces this, and set it equal to 0. You're supposed to get 0 out when you plug negative 1 in. So we're setting it equal to 0. I do the arithmetic, just powers a negative 1. We end up with negative 10 plus k equals 0. So k must be 10. We knew the form of f of x. Here it is. We just found out that k must be 10. So f of x itself must be of this form. And there's the desired function. There's a solution to that initial value problem. How would you check it? I'd differentiate this and make sure we got that. Pretty easy to do, and you can see it's correct. And I'd plug negative 1 in and make sure we get out 0. And that should be true by the arithmetic we just did. So there's solving an initial value problem. Is this a lot of stuff? Well, it's really just new vocabulary for the stuff we were just doing. We did this kind of thing a while ago, only we talked about it in terms of antiderivatives and graphs of functions passing through points. We've done this conceptual thing before. Now it gets the title of an initial value problem. It's antiderivatives and then algebra. Here's another one, but with trig functions in it. Suppose dv dt is 8t plus cosecant squared t, and v of pi halves equals -7. Solve. Find v as a function of t. Okay, we'll need to anti-differentiate. I'm not afraid of that. Can you anti-differentiate cosecant squared? Is cosecant squared the derivative of something? What's the derivative of cotangent? Negative cosecant squared? Yeah, I think that was it. So we'll see a cotangent, or maybe a negative cotangent. All right. Now, we've got the derivative, dv dt, as given. So v of t is an antiderivative of this function, 8t plus cosecant squared t. That is, v of t is an element of the indefinite integral. Let's shift over to indefinite integral notation. You want an indefinite integral of a sum. Okay, that's the sum of the indefinite integrals. I can bring constants out front. That's sum and difference rule together with the constant multiple rule. But like I said, let's gloss over writing that out at this stage. Can you integrate t? Sure. Add one of the exponent, divide, and we get t squared over 2. Can you integrate cosecant squared? I can look in the table, or I'm going to try to talk you into believing this. When we differentiate, forget the negative sign for a second. When you differentiate cotangent, you get negative cosecant squared. Negative, right, because it's a cofunction. You get negative cosecant squared. So when we differentiate cotangent, we'll get negative cosecant squared. And we got an extra negative that we've stuck in. Negative cosecant squared is cosecant squared. So yes, this is the right thing to get as the antiderivative of cosecant squared, or see part 5 in the table. And then we add the constant. It simplifies a very little bit. The 8 and the 2 cancel to give us a 4, but there you go. There's the indefinite integral. Are we done? No, that's, first off, that's not a function, and we're looking for a function. That's an indefinite integral. That's a set of functions, so that's a problem. And also, we haven't addressed the initial condition. So, knowing that v of t is in this indefinite integral set tells you that v of t is of the form 4t squared minus cotangent t plus some specific constant. I'm calling that constant k consistently. So there's the form of v of t. But I don't know what k is. But I got an initial condition I can use to find it. We left off with this statement on the previous slide. So we use the initial condition. V of pi halves equals -7. That's how we'll find the constant k. That's why they had to give us initial conditions. Otherwise, we can't find specific solutions. So we'll set v of pi halves. That would be 4 pi halves squared minus cotangent pi halves plus k. Yeah, here it is. We'll set that equal to -7. We were told equals -7. So let's see, we get pi squared over 4. That'll simplify to pi squared. Cotangent of pi halves, anyone? I think that's 0. Cotangent of pi halves is 0, so that's gone. And we get pi squared plus k equals -7. So k itself must be -7 minus pi squared. We found the constant. We'll plug that in here, and that gives us v of t. 4t squared minus cotangent t plus -7 minus pi squared. So there's v of t, the solution to that initial value problem. One more time. This is nothing new. We were doing this a while ago. We just weren't using the initial value problem lingo and the initial value solving for the constant stuff, unless we were looking at graphs that pass through specific points. Okay, here's one that's a second order differential equation along with initial conditions, a second order initial value problem. Second order because it talks about a second derivative. Okay, these could be quite involved. This one isn't. All we know how to do is anti-differentiate, and then only a very specific list of functions. So it better be related to that, and it is. You're told the second derivative of s with respect to t is 3t over 8. You're told the first derivative of s evaluated at t, the first derivative of s with respect to t evaluated at t equals 4 is 3. And you're told s evaluated at 4 equals 4. So we were given position, and I think they're getting at s representing position. Let me talk about it like that. It's just a function, but we've often used s for position. I think they're giving us the position at time 4. They're giving us the velocity at time 4. And they're giving us the acceleration at all times and asking us to find position as a function of time. Find s of t. That's what it means to solve an initial value problem. Find a function s that satisfies these conditions. All right, they gave us 2 initial conditions. This is very physical stuff. If I throw a baseball up in the air, can you tell me how high the baseball goes, or give me the height as a function of time? With enough additional information you can. We'll assume I'm at the surface of the earth, where acceleration, if you like feet and seconds, acceleration is negative 32 feet per second squared at the surface of the earth and near the surface of the earth. All right, then what's the trajectory of the ball? Well, you need more information. How hard did I throw it? That is, you need to know what the initial velocity was when I released it. Make more sense if I took t equal to 0 in this conversation. But when I released it, that gave it a certain velocity. Is that enough to tell you the height function? Well, there's one other thing to worry about. When I threw it up in the air, was I myself at ground level, or maybe I was on the top of a 3-story building? You need to know my initial height. So you need initial height, the height at which the ball was released, the velocity with which the ball was released, and the acceleration, and then you can determine how high the ball went. So you need 2 pieces of initial information. Yeah, because at the surface of the earth, you know the acceleration, it's constant. And from that information, you can solve for the height as a function of time. So if you think physically, it's not surprising it takes 2 initial conditions to deal with what's essentially a dynamics problem, throwing a baseball up in the air. So there's a physical argument that this makes sense that you'd have 2 initial conditions. And, well, if you don't buy that, let's try the algebra and you'll see we need 2 initial conditions. It's because we've got a second derivative, so we're going to anti-differentiate twice. That'll lead to 2 unknown constants. Well, that's why we got 2 initial conditions. So we're looking for s of t. Now, let's anti-differentiate 2 times. The first, we're given acceleration. We're given the second derivative. Well, let's find the first derivative based on the second derivative. ds dt is an antiderivative of the second derivative. If I were to differentiate the first derivative, I'd get the second derivative. So if I anti-differentiate the second derivative, I get the first derivative, plus or minus a constant. That is, ds dt is in the indefinite integral, where the integrand is the second derivative. So let's do that. Let's perform this indefinite integral computation. That'd be the indefinite integral of the second derivative, which was 3t over 8. So I'll put that there. If you like, I can bring the constant out front. Whoops, a little boo-boo there. I should have t's and switch it over to x's. No bad instructor here. Should have t's and all this. Another typo I will fix. 3/8 integral of t dt. I add 1 to the exponent and divide. I should be getting t's. And we'll get 3/16 t squared plus c. So the derivative is an element of this set. So we should have some constant, unknown constant. Let me call it k sub 1 for the specific constant. We need to find that specific constant. We've got an initial condition. We've got this function, the derivative, evaluated at t equals 4, and we're told that's 3. So we know the form of the function with t's. We know the form of the function, and we know an initial condition, just like we were doing before. Except we're going to have to do this twice because they give us a second derivative. Okay, so what we had was the initial condition. we had the form of the function. Good, I got the rest of it in t's. So it's a temporary insanity on x's. We have ds dt evaluated at t equals 4. It's 3 over 16, t squared plus k sub 1. T is 4. Plug that in. This is supposed to equal 3. Set it equal to 3. So let's see, 4 squared is 16. We get cancellation. That gives us 3 plus k sub 1 equals 3. K sub 1 is 0. So ds dt is 3 over 16 times t squared. I ain't looking for ds dt. We're looking for s of t. Well, the derivative of s is ds dt. So s of t is an antiderivative of ds dt. So we'll anti-differentiate this to get that. We're going backwards with differentiation a second time because we started with a second derivative. It's got to be done twice. And the same procedure. So now we need to integrate the first derivative, the 3 over 16 t squared. This becomes the integrand. We need to anti-differentiate that. Easy enough. You've got a constant, you got a power of t, add 1 to the exponent and divide, simplify, the 3's cancel. And we get t cubed over 16 plus c for the indefinite integral, telling you the s function is of the form t cubed over 16 plus k sub 2 for some constant k sub 2. Arbitrary constants for indefinite integrals, specific constants for functions. I will consistently use lowercase k's for the specific constants. I need a k sub 1 and a k sub 2 in this one problem because we had to anti-differentiate twice. Okay. We were also given the position. Well, s of 4 equals 4. I'm thinking position at time 4 equals 4. But we were told s of 4 equals 4. So we'll use that to find k sub 2. We'll plug 4 into the s function. We know the s function is t cubed over 16 plus k sub 2. So when t equals 4, you get this. Let's see, 4 cubed is 64 divided by 16 is just 4. We get 4 plus k sub 2 equals 4. K sub 2 is also 0. So s of t must be t cubed over 16 plus 0. Don't get used to these constants of integration being 0. Both of them were in this one. That's special. That need not be the case. Running low on batteries. So let's see this. We got time to do one more. Yeah, let's look at this one. Fingers crossed I get through the whole thing. I'll do this one even quicker. They give you a graph and they tell you these are graphs of functions whose derivative is x minus 1. And they're asking you, what's this red curve here? Find the equation of this curve. Well, we know the derivative is x minus 1, so functions of that form are in the indefinite integral of x minus 1. All right, so we'll integrate x minus 1. No problem. Add 1 to the exponent. We get x squared over 2 minus x plus c, telling you the form of the function, just like we were doing before. You were told in the picture that the function passes through the point -1, 1. So we'll plug -1 into the function, set it equal to the output of 1. That determines the constant. The constant's -1/2, and giving us the form of the function. Same technique as before on all the others. And that completes this section right before my laptop battery dies. And that completes chapter 4. So we'll pick up with the same idea of indefinite integrals and antiderivatives, and it'll play a huge role in chapter 5. So have a nice day. I'll see you in chapter 5.